Have you ever, stopped to think about how everyday things, say the pin holding part of a bridge up, or maybe the joints in a big pressure tank, are actually
Mhm.
designed? I mean, how they resist all these invisible forces? How do engineers make sure that the materials don't just, bend a little, but actually don't fail?
Yeah, it's a critical question.
Exactly. And that hidden world, the mechanics of materials, that's what we're going to pull back the curtain on today. Welcome to the deep dive. We're digging into a really fascinating chapter here, all about strain transformation, material property relationships, and theories of failure.
Hmm.
Our mission for you, it's simple. We want to pull out the key insights, the real nuggets of knowledge from this pretty dense stuff, give you a shortcut to understanding this hidden world.
Absolutely. We're going to break down how engineers figure out deformation, how they turn measurements into, well, useful data, and then how they link those deformations back to the material's own properties and, crucially, predict when something might give way yield or even break entirely.
Yeah, get ready for some genuinely surprising bits and maybe a few aha moments, because understanding this stuff, it's really the foundation for everything from, I don't know, your phone to a massive skyscraper. So we've set the scene, this big challenge of hidden forces, but to really get it, we need to understand the deformation itself first. Let's talk about strain. Okay, so when engineers talk about strain, what exactly does that mean? Like, what kinds of deformation are we actually looking at?
Right, so strain, at its heart, it's just a way to precisely measure how much something deforms. You put a load on something, it changes shape or size. We basically split this into two main types. First is normal strain, and
Mm.
sometimes you see it as epsilon,
Right.
but our source calls it P. Think changes in length or volume, like stretching a rubber band that's normal strain.
Okay, stretching.
Got it. Then there's shear strain, that's gamma, the copening. This is more about changes in shape, like an angle changing, maybe without the volume changing much. Imagine pushing the top of a square box sideways so it leans over into a parallelogram. That
Yeah.
change in the corner angles, that's shear strain.
Ah, okay, the twisting or skewing kind of deformation.
Exactly. Now, in full 3D, you technically have six components. PX, PY, PS for normal strain in each direction, and then guxy, gex, guzzy for the shear angles between those axes. But honestly, for a lot of practical work, especially looking at surfaces, we often simplify things down to plane strain, just focusing on what's happening in a 2D plane, PX, PX, and guxy.
Okay, now here's where it gets a little, well, maybe counterintuitive. You've got plane stress forces acting in a plane and plane strain deformations happening in that plane. They sound like they should be perfectly linked, right? But one doesn't automatically cause the other.
Wait, really? Why not?
It's because of something called the Poisson effect.
Plus effect. Okay, so it's like if I push on a block in, say, the X and Y directions, it might still squish or stretch in the Z direction, even though I didn't push there directly. Is that the idea? That's a perfect way to think about it. Yes. Applying stress just in the XY plane can still cause a normal strain, thus in that Z direction. It's because the material's dimensions are interconnected. Stretch it one way, it tends to get thinner in the others. It's this inherent property.
Okay, that makes sense. So even though you said perfect plane strain is rare in the real world because materials usually can deform a bit in that third dimension, why is analyzing it still so critical for engineers?
Ah, great question. It's crucial because plane strain analysis is the key tool that lets engineers take measurements from strain gauges, which they usually stick on the surface of a part, and use that data to figure out the plane stress at that point on the surface.
I see. So you measure the strain on the outside to understand the stress, the forces happening right there. It's like reading the surface to know what's going on underneath in a way.
Precisely. It bridges the gap between what we can easily measure and the stress state we need to know for design. Hashtag the power of transformation equations.
Okay, so let's say you've measured the strain, POX, POY, GUXY, in one orientation. That's useful, but structures are complex, forces come from different angles. How do you figure out the strain if you mentally rotate that little piece of material? That seems like the real challenge.
Exactly. And that's where strain transformation equations become absolutely vital. They let you calculate the strain components, px, pi, y, psi, for any rotated orientation, if you know them for one orientation.
Okay, so there are equations for that. Are there rules, like for sines and angles?
Yes, definitely. The conventions are important. Positive normal strain means the material is elongating, stretching out. Positive shear strain means an internal angle in the material is getting smaller than 90 degrees. And a positive angle, theta, for rotation is always counterclockwise. And here's a really neat thing, a bit of mathematical elegance, you could say. The equations for transforming stress, like or SOHCAHTOA, are mathematically almost identical to the strain transformation equations. You basically just swap stress for normal strain, and you swap shear stress for half the shear strain.
Wait, half the shear strain? Why half?
Ah, that's a detail related to how the equations are derived, often linked back to the tensor nature of strain. But the key takeaway for engineers is this direct correspondence. It means if you understand stress transformation, you practically already understand strain transformation. It simplifies things a lot.
That is a handy shortcut. Okay. So once we can transform strain, we can start looking for special orientations, right? Where the deformation is maybe simpler. Let's talk about principal strains. What's special about them?
Principal strains represent orientations where the deformation is purely elongation or contraction. There's no shear strain happening along these axes. Think of it as finding the directions where the material is just stretching or squishing straight with no skewing or twisting involved.
So pure stretching or compressing.
Exactly. And for isotropic materials, materials with the same properties in all directions, which covers many common engineering materials, these principal strain axes are the same axes as the principal stress axis.
Ah, so the direction of maximum stretching lines up with the direction of maximum pulling stress, essentially.
It shows that fundamental link between the applied loads and the resulting deformation pattern.
Okay. And what about the maximum shear strain? Is that on the same axis?
No, typically not. The maximum in-plane shear strain occurs on planes that are usually oriented at 45 degrees to the principal planes. And importantly, on these planes where shear strain is max, there's also usually an average normal strain present as well. It's not zero normal strain like on the principal planes.
Okay, so you have principal strains, maximum stretch, no shear, and maximum shear strain, max twisting, happens at 45 degrees to the principal directions. How do engineers keep all this straight and visualize it?
That's where Mohr's circle comes back into play. Just like it's used for stress, it's an incredibly powerful graphical tool for understanding strain transformation.
Right, more circle. How does it work for strain? Is it the same setup?
Very similar, but with one key difference in the vertical axis. You plot normal strain, P on the horizontal axis, positive to the right, just like normal stress. But on the vertical axis, you plot half the shear strain, and by convention, positive 2 is plotted downwards.
Downwards, okay, that's a specific convention to remember.
It is. Once you plot your initial known strain state, PXE and maybe pi KZ2, as points on this graph, you draw a circle through them centered on the p-axis. From that circle, you can find everything graphically. The points where the circle crosses the horizontal p-axis. Those are your principal strains, P1 and P2.
Makes sense, because shear strain, the vertical axis, is 0 there.
Exactly. And the very top and bottom points of the circle, their vertical coordinates, give you the maximum in-plane shear strain. Well, half of it, got x2. Plus, you can find the strain state for any other orientation just by rotating around the circle by twice the physical angle. It gives you the whole picture at a glance.
That's incredibly useful. Beats plugging numbers into complex equations over and over again.
It really does help build intuition about how strain behaves.
Okay, so this brings us to a really practical problem. You mentioned strain gauges measure normal strain, T. You stick them on a surface, stretch it, and get a reading. But you also said you cannot directly measure shear strain gauger.
No.
So how do engineers get doxy if they can't measure it? How do they get the full picture for plane strain?
Ah, yes. This is where some real engineering cleverness comes in. The solution is the strain rosette.
A rosette, like the flower.
Sort of, in the sense that it's an arrangement. It's not just one strain gauge, but a cluster of 3 electrical resistance strain gauges precisely positioned on the surface at specific angles relative to each other.
3 gauges in one spot. Okay. Why 3 and what angles?
3 is the minimum you need to solve for the 3 unknowns in plane strain, Px, Py, and tuxi. The most common arrangements are the 45-degree rosette, gauges at 0 degrees, 45 degrees, 90 degrees, and the 60-degree rosette. Gauges at 0 degrees, 60 degrees, 120 degrees.
And how does measuring normal strain in 3 different directions tell you the shear strain? That seems like magic.
It feels a bit like it, but it's just clever application of the transformation equations we talked about. Let's say the 3 gauges give you readings Pi, P, and Pc. Each reading represents the normal strain in the direction that specific gauge is pointing. You take those 3 known values, Pi, Pv, Pc, and plug them to 3 instances of the strain transformation equation, one for each gauge's angle. Now you have a system of 3 equations with 3 unknowns, Ps, Pi, Bc. You can solve them simultaneously.
Ah, simultaneous equations. Okay, I see. You use the known normal strains at known angles to algebraically find the unknown base strains, including the shear.
Precisely. For example, with a 45-degree rosette, the solution is quite neat. Px is just the reading from the 0-degree gauge,
Yeah.
PAC. Pi is the reading from the 90-degree gauge, PC. And the shear strain doxy comes out as 2 times the 45-degree reading, PB, minus the other two, Ppop plus PC.
Wow.
For the 60-degree rosette, the equations are a bit more complex, involving things like square roots of 3. But the principle is identical. 3 measurements let you find the 3 unknown components.
That is genuinely ingenious. It's a perfect example of bridging theory in practice. You can't measure something directly, so you measure related things and use the theory to calculate the missing piece.
Exactly. It's fundamental to experimental stress analysis. Okay, so we understand strain, how it transforms, how we measure it. Now let's connect it back to the stresses causing it. This is where material properties really matter, governed by what's called the generalized Hooke's law.
Hooke's law. I remember that from basic physics. Force is proportional to displacement. FPX.
Sort of the 3D, more complex version of that, yes. For a material under triaxial stress, meaning forces in x, y, and z directions, the strain in, say, the x direction, Px, isn't just caused by the stress in the x direction. Thanks to that Poisson's ratio we mentioned, it's also affected by the stresses in the y and z directions. They cause lateral contraction or expansion that adds to Px.
Right, everything's interconnected. What about shear?
Shear is simpler in this respect. Shear stress in one plane, like texy, only causes shear strain in that same plane. It doesn't directly cause shear strain in the other planes, like the extra keys. And it's crucial to remember these key material properties. Modulus of elasticity, E, stiffness and tension compression, shear modulus, G, stiffness and shear, and Poisson's ratio, the contraction ratio, they aren't independent. They're linked by a fundamental equation. G ilio 1, 2, 1 plus 2.
So if you know 2, you can find the third. Okay, now what about the overall volume change when a material deforms? Does it get bigger or smaller?
Good question. That relates to dilatation or volumetric strain. It's just the change in volume divided by the original volume. And interestingly, it's caused only by the sum of the normal strains, Px plus pi plus P's. Shear strains distort the shape but don't change the volume, at least for small deformations.
Okay, and is there a property that measures resistance to volume change?
Yes, that's the bulk modulus, usually denoted by K. It measures how much pressure you need to apply uniformly, like hydrostatic pressure underwater, to cause a certain amount of volume decrease. And here's where Poisson's ratio pops up again in an interesting way. The theoretical maximum value for E is 0.5. If a material actually had E equals 0.5, its bulk modulus K would become infinite.
Infinite.
Meaning it would be perfectly incompressible. No volume change at all, no matter how much pressure you applied. Real materials get close, like rubber, but nothing's perfectly 0.5.
Fascinating. Okay, so understanding all this strain, stress, material properties, it all leads up to the big one, right? Predicting when something actually breaks or fails.
Exactly. That's the ultimate goal for a design engineer. Predicting failure. For ductile materials, like most steels or aluminum alloys, failure is usually defined as the start of yielding permanent deformation. For brittle materials like cast iron or glass or concrete, failure means fracture, literally breaking apart, often suddenly. So we need theories to set upper limits on the stresses material can handle.
And I imagine it's not simple.
Definitely not. It's a really crucial point. There's no single universal failure theory that works perfectly for every material under all conditions. Temperature matters. How fast you apply the load matters. Even the shape of the part matters. And critically, to use any of these theories correctly, you absolutely must first determine the principal stresses acting on the material at the point you're worried about.
Right, those maximum normal stresses we talked about earlier. You need those as input.
Yes. Predicting failure is complex. Even with the best theories, there's always some uncertainty, especially with brittle materials. Have tag theories for ductile materials. Yielding. Okay, let's look at ductile materials, first things that stretch or bend before breaking. There are 2 main theories we use to predict when they'll start to yield. First is the maximum shear stress theory, also known as the Tresca theory.
Tresca, okay. What's the idea behind that one?
It's based on observation. When ductile materials like steel yield, you often see these faint angled lines appear on the surface called Luder's lines. They show that yielding actually happens due to microscopic slipping along planes inside the material, typically at about 45 degrees to the main stress. And what causes slipping? Shear stress. So Tresca's theory says yielding starts when the absolute maximum shear stress anywhere in the material reaches the value of shear stress that causes yielding in a simple tensile text.
Which is related to the yield strength and tension, right?
Exactly. It's typically the tensile yield strength divided by 2. So 10 max by 22. If you plot this criterion on a graph of principal stresses, it forms a hexagon shape.
A hexagon. Okay. What's the other main theory?
The other big one is the maximum distortion energy theory, often called the von Mises theory.
Von Mises. Different idea.
Yes, a slightly different physical basis. This theory proposes that yielding doesn't depend directly on the maximum shear stress, but rather on the energy stored in the material that causes its shape to change the distortion energy. It separates the energy into two parts: energy causing volume change, hydrostatic, and energy causing shape change, distortion. Von Mises says yielding occurs when the distortion energy per unit volume reaches a critical value, again related to the yield strength from a tension test.
And what does that look like on the stress graph?
This one plots as an ellipse that encloses the Tresca hexagon.
Okay, a hexagon versus an ellipse. They sound pretty similar if the ellipse contains the hexagon. How do they compare in practice? Which one do engineers usually use?
They are often quite close, especially for many common stress states. However, experimental results tend to show that the von Mises ellipse theory matches reality a bit better for most ductile materials. It's generally considered more accurate, particularly in situations involving pure shear, where it predicts yielding at a stress about 15% higher than Tresca, which aligns better with tests. So von Mises is very commonly used in design.
Okay, so von Mises is often preferred for ductile stuff because it seems to match experiments slightly better. Hashtags tag theories for brittle materials,
Yeah.
fracture.
Right. Now let's switch gears to brittle materials, things like cast iron, concrete, some ceramics, glass. These tend to fracture suddenly with very little warning or yielding.
Right, they just snap.
Exactly. For these, the dominant theory is often the maximum normal stress theory, sometimes called Rankine's theory.
Maximum normal stress now, not shear.
Okay, correct. This theory is very straightforward. It says fracture occurs when the maximum principal tensile stress anywhere in the material reaches the material's ultimate tensile strength, SALT, which you'd measure in a simple tension test. It basically ignores the effect of other stresses, like compressive stresses. If the biggest pull hits the limit, it's predicted to break.
Does that match how brittle things fail?
Often, yes.
Hmm.
For example, if you twist a piece of brittle chalk until it breaks, the fracture surface isn't usually perpendicular to the axis. It's often helical, at about 45 degrees.
Why 45 degrees?
Because in pure torsion, the maximum tensile stress actually occurs on planes at 45 degrees to the axis of twist. So the chalk breaks in tension even though you were twisting it. This theory, Rankining's, plots as a square on the principal stress graph.
A square this time. Okay,
Yeah.
is that the only theory for brittle materials?
Not quite. There's also Mohr's failure criterion, which is particularly useful when a brittle material has very different strengths in tension versus compression. Cast iron is a classic example, much stronger in compression than tension.
How does Mohr's criterion work? Is it related to Mohr's circle?
It is. It uses Mohr circles from experimental tests, typically tension, compression, and maybe torsion tests, to define a failure envelope on the stress graph. You plot the circles representing failure in these simple tests, and then you draw a curve or lines that are tangent to all these circles. That curve is the failure envelope. Then for any complex stress state, you draw its Mohr's circle. If that circle touches or goes outside the failure envelope, failure is predicted.
I see. It's a more empirical approach, tailored to the material's specific tested strengths.
Exactly. But, and this is a really important but for brittle materials, predicting fracture, especially tensile fracture, is inherently tricky.
Why is that?
Because brittle fracture is often initiated by tiny microscopic flaws, little voids, cracks, inclusions that are inevitably present in the material. The size and location of the worst flaw can dominate the strength. And these flaws vary randomly from sample to sample, so there's much more scatter in the strength of brittle materials compared to the yield strengths of ductile ones.
So these theories are guides, but you need to be extra cautious with brittle materials. Use bigger safety factors.
Precisely. Significant caution and often larger factors of safety are essential when designing with brittle materials, especially under tension. The theories provide a necessary framework, but understanding their limitations is critical. Hashtag outro.
Wow. Okay, so we've really journeyed through this intricate world of strain today. We looked at how it transforms depending on orientation, how engineers cleverly measure it using rosettes, even when they can't measure shear directly.
And how it all connects back to the stresses and the fundamental properties of the materials themselves.
And most importantly, we dove into how engineers actually try to predict failure using these different theories. Tresca and von Mises for ductile yielding, Rankine and Mohr for brittle fracture. It's all about ensuring safety in the things we build and use.
Absolutely.
Yeah.
This isn't just abstract theory locked away in textbooks. It is the absolute bedrock of structural integrity. Everything from a tiny medical implant inside someone's body to the tallest skyscraper relies on these principles. It's all about designing things that don't just function, but function safely and predictably, even when pushed.
So maybe next time you lean against a bridge railing or you see one of those big industrial pressure tanks, take a second. Consider that invisible dance of strains and stresses happening inside the metal and the careful calculations that went into making sure it stays solid. It makes you wonder what other everyday objects heavily rely on these precise kinds of calculations for their design.
It's almost everything, really, when you start to look. And if you, listening, found this deep dive interesting, if you want to understand more about how engineers ensure things are built to last, maybe you have sources or topics you'd like us to explore, send them our way.
Yeah, we love tackling new material and helping you get informed, one deep dive at a time.